All right. So yeah, I'm going to talk about new forms of policy gradients for model-free estimation. And there will be a bit of math, but I will try to go through them slowly and hoping to still make it within 20 minutes. So bear with me. So this talk is about control with policy gradient methods, and policy gradient methods, you can contrast them with value-based control methods, which can be seen as mechanisms to achieve a fixed point of the Bellman equation for action values. And in those methods, policies are derived based on estimated values. And in contrast, policy gradient methods, they directly represent the policy as a parameterized function, such as a neural network, and then they directly estimate the gradient of a policy objective. And that way, it is more of a natural way of doing control. It directly tries to optimize a control objective. And especially for continuous control, continuous actions, it's a suitable way of doing control. So let's start this setup right away. We are talking about an agent that's interacting with an environment with continuous states and actions. The agent at, by the way, the time is discrete here. So the agent at state ST takes an action AT according to a parameterized distribution pi. So it depends on the state and it's parameterized by parameter vector theta. So theta is what we want to learn with policy gradient methods. If you change it, the distribution will change. So that's the distribution of the action. And then in return, the environment provides the next state and reward in the next step. And let's, for simplicity, consider undiscounted episodic task with the initial state distribution D0. Now, what is the goal here? The agent's goal is to maximize future cumulative reward, which is also known as the return. Now, return is a random quantity. So if we want to get a sense of a true objective that the agent needs to optimize, then we need to consider all the randomness here. So we want to talk about expected return that the agent needs to maximize. So the expected return for a given state, and then from then on, following a policy pi is known as the state value function for S. And then the true objective can be written as j theta, which is the expected return, really the value function over the initial states. So that's what we are trying to maximize here, which makes sense for episodic tasks. And how are we going to do that with policy gradient methods? So policy gradient methods, they estimate the gradient of the policy objective, usually in a model-free way. Now, we're talking about policy gradient. I want to quickly define or redefine what I mean by policy gradient. Here, I really mean ways to take the gradient of the policy objective. So that's what I mean by policy gradient. All right, so then really what we are trying to do here is to write the gradient of the true objective in an expected form, preferably under a distribution that is aligned with the experience of the agent, and have a random variable that we can calculate based on samples without recurring a model. If we have that form, then we can use that sample to make updates to the policy parameters using stochastic gradient descent. So that's basically the form of policy gradient methods. Now let's look at the original way of writing the gradient of the true objective. Right, so the original way, note that the objective can be written as we already saw in this integral from expectation of the value function, but the first part here is the initial distribution doesn't depend on the policy, but the value function does. It is induced by the policy. So then the gradient can go inside the integration past and even go past this initial distribution. But then we'll have to take the gradient of the state value. Right? So that's what we have to do, and it's hard to do because the state value, it implicitly depends on the policy parameter theta, not directly. So it's not in dependent in a form that an agent can clearly see the dependence and calculate the gradient. So, but however, we can further expand state value in terms of action value function. So if we expand it, this is the relationship. Good thing about that is it has two terms, where the first one is the action likelihood, which the agent itself maintains. This is accessible to the agent. So then we can basically use the product rule to have this form. Using the product rule, we have the gradient of the first term and then the gradient of the second part, right? So gradient of the first part in this first term, if you think about it, this is something the agent can estimate. The agent can estimate the action value as returns, and agent has access to the action likelihood, and it can take the gradient. In the second part, we have again the gradient of the of a value with respect to the policy parameter theta. So it's kind of like a same as this. It's hard to estimate. But what we can do is we can continue to unroll it into the future. The action value, we can continue to unroll it into the future, and it is shown that if we continue to do that, we are going to get this first term, this more convenient term, again and again, weighted by different probabilities, which end up being proportional to the on-policy distribution, which is convenient because that's the distribution of state that the agent will experience. So that's great, because then we can write this form as an expectation of a random variable that can be completely calculated without needing a model. So return, the agent can observe, and these are maintained by the agent. So I'm taking the gradient of the action likelihood. And this is also known as the reinforced estimator, and arguably the first unbiased policy gradient method. So many policy gradient methods, reinforced, standard active critic, PPO, ACER, they are based on this form of writing the policy gradient. I will refer to this form of policy gradients as the likelihood gradient. Here we are taking the gradient of the likelihood. So I need to give a name because we are looking for other forms. So there will be different kinds of policy gradients. Okay. So what do we have now? We have a nice form from which we can have model-free estimation and some facts about it. That yeah, it can be estimated in a model-free way, and it requires stochastic policies, right? So you need to take the gradient of likelihood. So you need stochastic policies to have this gradient estimate. And some intuition how it works, you can think of it as adjusting the action likelihood proportionally to the ensuing returns. You take an action, you see the ensuing return, and based on that proportionally, you change the likelihoods or action probabilities, really preferences. So you can imagine that as it works this way, it will rely on many samples to estimate a reliable direction. So these are some facts. Now the question is that is this the only way of writing the policy gradient? Is there any other way? So there's a question, and we do have another way. It is given by the deterministic policy gradient theorem, and it is for deterministic policies. For deterministic policies, you don't have the gradient of likelihood, but then the action value becomes differentiable with respect to its second argument, which is the action. And this is something you can actually estimate based on samples if you are estimating the action value using a function approximator, which is taking a continuous action as an input. So you can differentiate basically with respect to the second argument. And so this was derived for deterministic policies. And the intuition here is that this way of estimating the gradient, it will adjust the policy parameters by directly moving the action toward high value estimates. But you can change the action, it will change. You don't have to really look at the whole rollout to understand what is the consequence of an action. You can directly look up using your action value estimate. You give action as an input, you readily see the estimate, action value estimate, and then as it's continuous action, you can smoothly move the action value estimate moves, and that way you can move the action toward a region where you have higher value. Okay, so that's how it works, and it has at least empirically shown that it has more sample efficiency. And the thing is that the issue is that this is derived for deterministic policies for which a sample-based estimation is a bit difficult. So that's one issue. Now I'm going to refer to this form of policy gradient as the action value gradients. Okay, so these are action value gradients. They do not take likelihood gradients. All right. So
we have a couple questions here.
Yeah, can I take it after the talk?
Okay.
All right. All right. So then this looks like a different way of writing the policy gradient. It's a different way. It cannot be subsumed by the original way. Now, it's so separate that it seems like it's for deterministic policies. A natural question would be, can we have action value gradients for stochastic policies? So in our recent work, we show that it is possible. And I'm going to go through the derivation now. All right, so bear with me. Let's start over. We write the objective again in terms of action values. Now, again, we have the likelihood, action likelihood. So the distribution is back. And we know that we can push the gradient inside here. But now, what are we going to do here? If we start to apply product rule, then we'll end up having likelihood gradient, which we are trying to avoid, right? So instead, what we can do is we can change the variable, action variable, to kind of make the likelihood disappear so that we can avoid taking the gradient of likelihood with the hope that we'll end up having action value gradient. So the action, if it can be written in terms of another random variable, which has a base distribution that does not depend on the policy parameters. There are distributions like that. For example, if the action is distributed according to normal distribution, then it can be equivalently written as a function of a standard normal random variable, which is not a function of policy parameters. So if we have this form, we can use it to write this integral where instead of a, we use epsilon, change of variable. So we change the variable, these two are equivalent. Now, why we did that? To make the action likelihood disappear. Note that this is not anymore a function of theta. So the gradient can be pushed inside. And now we have to take the gradient of the action value. Now this one a bit different. This one is differentiable through two pathways. In the original one, we had this inducing policy. It's also, at the same time, it's also differentiable with respect to its second argument, the action. So we do that. Use the chain rule. This one is with respect to the second argument, and this one is the original way. And we know how to deal with that. We unroll it into the future. and it gives a term that's proportional to the on-policy distribution. And first term is what we were actually looking for. This is what we call action value gradient. It can be estimated from sample if you are estimating action value using a function approximator. So we ended up getting that. So we're almost there, except one problem is that we want to write it in terms of our expectation over actions, and action is gone here. We don't have action. So we need to bring back action. So we can change the variable again. We can write epsilon in terms of action back, but G is the inverse function of F. If we do that, then pi is back. All right, so pi is back. Now we can write it in terms of an expectation. Of course, approximately, because you have to estimate the action value, and the quality of this gradient estimate depends really on the quality of the action value estimate. Now, but we answered the question whether we can have action value gradients for stochastic policies. And look how we achieved it. Pi was here, it disappeared, gradient went inside, and then pi came back. It's if you saw the Matrix movie, it really reminds me of Neo dodging the bullets. The gradient is the bullet, and pi is Neo. So it really avoided it and came back. So that is the technique that was required to show it. Now this allows us to have this is really the action value gradient is a separate way of writing the policy gradient, separate from likelihood gradient. And now we can show that the deterministic policy gradient is just a special case. And moreover, some existing policy gradient methods, such as arithmetic DDPG TD3, which were not unified by one particular way of writing the policy gradient. Now they can be obtained using action value gradients using this theorem. So this exercise gives us a better understanding of the landscape of policy gradient methods. So we had these algorithms, reinforced PPO, ACER, all actions method. We were able to unify them under a theorem based on likelihood gradients. But we had other algorithms, they were not unified. Now they can also be unified under a theorem based on action value gradients. So this exercise also allows us to ask interesting questions like this one. Can we have model-free policy gradients through reward gradients? Right, so it's a likelihood gradient, it's an action value gradient. How about we take the gradient of the reward? Reward estimation can be easier, more stable than value estimation. For example, the reward as a function of actions does not depend on the policy, right? So this way, think about action value estimate. We are doing control, the pi is changing over time. The action value estimate is changing over time. That's not true for reward function as a function of action. So this way it can even be estimated a priori. So we're really talking about taking the gradient of the reward with respect to its second parameter action. So that's what we want to do. Of course, we're going to estimate reward. Is that possible in a model-free way? So what is the situation in the literature? Do we have anything? It turns out there are methods that take reward gradients, but they're model-based methods. And it makes sense. If you're learning a model, you will actually estimate the reward using a function approximator. But that's not what we are looking for. What we are looking for really is a new category that utilizes reward gradients, right? So, but it's on the right side of this barrier. So all the methods on the right side, they are model-free. On the left side, they are model-based. So we're looking for this new category, model-free policy gradient methods that utilize reward gradients. We don't have any. There is none. So turns out that we can have. So by repeating this exercise now, we found that we can have a model-free estimate that utilizes reward gradient. It also combines likelihood gradient. And note that it's not an interpolation. If you drop either of these two terms, it is going to be biased. It's just wrong. It will be wrong. You need both. So this is the first model-free policy learning estimator that uses reward gradients called reward policy gradient. We call it reward policy gradient, RPG. This is a work in collaboration with my PhD student, Qingfeng. We'll talk about it next week. So RPG is the first occupant of this category, right? So now I'm going to conclude. In conclusion, we now have a better understanding of the landscape of policy gradient methods. We can have action value gradients for stochastic policies. Most existing policy gradient methods can be derived or directly connected to policy gradient theorems for either likelihood or action value gradients. And we have a whole new category of algorithms that estimate policy-free, model-free policy gradients using reward gradients. Thank you.
Thank you, Rupam. So I guess now we'll open for questions.
Yeah. Questions?
Well, I'll start with a non-question, which is just that I thought that was really, really elegant, which you presented.
Thank you.
Yeah, good job. Wonderful.
Awesome.
Yeah, I had a doubt. I'm not sure. But this step that you had where you replace action with a noise, that is a reparameterization trick, right? That you use in that case. And that might not be applicable for all the distributions.
So I'm not sure it's clear. So we have to look for distributions. Yeah. So the question is, it's really about the applicability of this new theorem, new estimators. What we have here in the original case, the original gradient estimate, it basically can be applied for any stochastic policy. Is that also true for the new one? But obviously you have restrictions. It has to be continuous action. That's why it's really applicable. And we also need this kind of transformation, right? You have to represent the action in terms of another random variable that does not depend on theta. So you might be able to do it generally for distributions, but it might not have this kind of easy form, right? So a closed form relationships may not be obtained or difficult to obtain. So I'd say that it's not as easy as it is with normal distribution for all distributions. Thanks, Val. And another point is that he mentioned that this is basically what I use. He said that this what I used is basically a reparameterization trick. And I'm really glad that I gave the whole talk without talking about that trick. Really, it was not needed. I did not need to talk about trick or reparameterization. First is, I would say, I find it non-educative when you talk about trick. And second is hard to say. And I think it's just better that I didn't need to talk about that. But it's true. This kind of technique, it has a name. It just makes it more obscure. I have to understand what's going on when we say that. Any other question?
But is this mic better? Sorry for that.
Say it again.
Is the mic better now? Yeah. The reason I asked about the because it's very common and like it's one of the ways where you deal with stochastic policies. So I was just wondering. Yeah. And one more thing, I'm not sure. So the place where you have to take a gradient for the Q function, is there any way where we can is there any way that we can do that? Like maybe with successor features, having a parameterized successor feature, or like some way to make that as a analytical gradient.
You're talking about this one?
Yeah.
Right. Maybe.
Like, have you thought about it? That's what I was thinking right now.
Not fully. Not fully. No. Yeah, Rich. You're muted.
Now I have a couple of real questions. So this all makes sense when your randomness is like you're adding in a Gaussian. But this sounds like it might be is this a limitation on the structure of the random policy? Feels like
right. So basically you have to think about the distribution that you choose and see whether you really have this kind of simple relationship. So for some distributions, it's figured out. We know we have this kind of relationship. It's not confined to only normal distribution.
Also, I think, sorry, go ahead, sorry.
Second question, yeah, Rich.
So in the what do we call it? The
likelihood gradient.
Likelihood gradient. You only rely on the action values having the correct values, or being approximately the correct values. Whereas now it seems like you're going to rely on them having the right derivatives.
Right.
Yeah.
Yes.
Yeah, like
that's
if you had
a bit of a problem.
Yeah. So yeah, what do you think about that? Is that a problem? That's the question, I guess.
I think so. I think yes. If this gradient, if we don't have a good estimate of action value so that the gradient is correct, then we are basically in trouble. So
could we adapt our learning mechanism so that it would directly try to make the gradients right?
interesting question. So think about how to. Yeah. So try to. I see what you mean. I think it's a great point. I don't recall anyone doing it in this context. Michael, another PhD student of mine, was working on directly estimating the gradients more correctly in a different context, in the robotics context. So people do that. So that kind of techniques might be helpful here. That's a very good point. Is Michael here? No, it's okay. Yeah, go ahead.
We have a question in the chat. Isn't it the same with DDPG?
It was a follow-up question on what Rich just said about the fact that we are trying to estimate the gradients more accurately. Well, it's the same with action value-based gradients, right? We're trying to have this gradient of action value well estimated. And so if the problem that I have is, does it make it better, the fact that you have to both have the gradient of your action value accurate and the rewards, the gradient of the rewards that are accurate for your reward policy-driven method, or is it worse to need to have both at the same time?
So the reward policy gradient actually does not need or use action value gradient.
Yeah, sorry, it's a likelihood. The question is the same. So the fact of having to estimate both, so it's not the gradient of the value. So if you have to estimate both the rewards, the gradient of the rewards, sorry, accurately, and the value accurately to compute your updates, isn't it worse than just like the action value or something like that?
Well, for the likelihood gradient case, we understand a bit better what we need here. You can have unbiased estimates. So let's go back to the likelihood gradient. You basically need an unbiased estimate of the action value, which you have, the return, right? So which you cannot use for action value gradient because return is not in a form that you can differentiate with respect to action. So likelihood gradient form, I would say, has less of a problem in terms of estimating the action value. For action value gradient, we have more of a problem.
I guess my problem was not with the bias estimate, but more with the variance of it. If you were to estimate, when you try to, that was the problem with reinforced, right? The variance was too high, and so it was harder to learn. And so what I feared here is that you had to both the variance of trying to estimate, your return and the but not bias. I don't know if it will be biased, but when you try to estimate your gradient of rewards that you will have to learn because you don't have the model. If you had the model, the gradient would be exact for the rewards. But if you try, you will need to learn this reward model and to take the gradient of that, right? And so
right. I think you are having the right focus, which is about the reward. Really, here we need actually to worry about, and same goes that the estimate has to be good. The thought is that we might have a better situation than action value gradient when we are using reward gradient. So that's what we are thinking.
Okay, thank you.
All right, thanks.